Hello everyone, I am Jie Luo from China Academy of Telecommunications Technology. It is my honor to give a presentation here. The title of my paper is Distributed Deep Reinforcement Learning Based Mode Selection and Resource Allocation for VR Transmission in Edge Networks. Now I will talk about the paper in the following 5 parts. Introduction, System Model, Distributed Game Theory-Based Deep Reinforcement Learning, Simulation Results, and Conclusion. The first is the introduction. The main problem we focus on is that wireless virtual reality is expected to be one of the most pivotal applications in 5G and beyond, which provides an immersive experience and will greatly renovate the way people communicate. It is crucial for VR service to maintain an immersive experience for VR users. So how to provide a high quality of experience, QoE, and huge data rates is an important problem to be considered. Thus, we came up with solutions as follows. A joint optimization problem of the mode selection and resource allocation is formulated to maximize the QoE of all VR users, and we propose a distributed game theory-based deep reinforcement learning (DGTB-DRL) algorithm to conquer the above highly competitive problem, which can achieve a Nash equilibrium rapidly. In this paper, we consider a mobile edge network composed of Y cloud nodes, M edge nodes, and U user equipments as a cloud edge and collaborative framework, as shown in Figure 1. The original VR game resources are centrally managed by the cloud server on the cloud nodes. Equipped with edge servers, edge nodes serve as access points, are distributedly deployed in the VR environment on a large scale, and nodes are defined as VR headsets worn by real users. Considering the different quality of service requirements and the computation capability of different users, the VR user can choose 3 modes to transmit the content: cloud mode, edge mode, and local mode. The cloud nodes transmit the content directly in cloud mode, while the edge nodes serve users simply in edge mode. Especially, there are femtosed base stations for short-distance transmission in local mode. Assume that different transmitting nodes may associate with different sets of end nodes with several shared orthogonal channels. All transmitting nodes share the same downlink spectrum, and there is interference among cloud nodes, edge nodes, and phantom base stations. As a result, we have the total downlink data rate of the ith user, which is calculated by this expression. According to reference 9, the time of video storing should be kept at a low level to enhance the user's experience. We convert logarithm to linear weighting and make a reasonable migration assumption. We define the time average storing probability and the time average bitrate. Therefore, The average QoE for the ICE user at processing period T can be calculated as the following expression. Our goal is to develop an effective join mode selection and resource allocation scheme to maximize the QoE of the VR users. The optimization problem can be formulated as follows. The first constraint, C1, denotes the mode and the channel limitation. The second constraint limits the computation resource of computing servers. And the third constraint, C3, means that each user should achieve the minimum QoS threshold. It is worth noting that the action space of the issue increases exponentially with the growth of the number of transmitting nodes and channels. It is a great challenge to find a globally optimal strategy for the join mode selection and resource allocation problem. Besides, the traditional centralized learning method may need global information of all nodes to achieve the optimal solution. Hence, we develop a distributed game theory-based deep reinforcement learning method for the optimization problem in the mobile edge network. Figure 2 shows the procedure of the purpose algorithm. Mode selection action taken by users may consume cost. The reward of the ICE user should be given as the QoE utility minus the action selection cost. When the ICE user makes a decision and takes the action, it receives an immediate reward. Assume that the whole system is stationary. The policy is defined as a time-invariant mapping, and the long-term reward can be formulated as the second one. The overall algorithm is illustrated in algorithm 1. Then we set a simulation scenario. The simulation parameters are summarized in the table. We consider a mixed VR scenario consisting of 2 cloud nodes, 8 edge nodes, and 30 end nodes. And the related transmission radiuses are 500 meter, 100 meter, and 30 meter respectively. In our experiments, the deep neural networks are composed of an input layer, 3 hidden layers, and an output layer, using the ReLU for activation function. We initialize 500 episodes and 500 steps for a trial, 8 for mini batch size and 500 for replay memory. The epsilon greedy policy is utilized linearly from 0 to 0.9. Next, I will talk about the simulation results. First, we compare the performance of different learning rates for our algorithm. Figure 3 demonstrates the training efficiency with varying learning rates. As the learning rate decreases, the speed of convergence increases, and it shows that all users satisfy the QoS threshold through exploration and exploitation. However, when the learning rate is set to be 0.0001, the learning convergence becomes unstable at the end of the process. Then, we evaluate the performance of our algorithm with different optimization strategies. As shown in Figure 4, at the early phase, training steps are very large in all cases. As the number of episodes grows up, the RMS probe optimizer and adaptive gradient optimizer shows better convergence than Adam. Secondly, we simulated different scenarios in Figure 5. The number of AND nodes is varied in this experiment. The curves indicate that the efficiency of our algorithm is decreasing with the growth of the number of users. That is, as the number of users increases, it takes more time for agents to get their optimal action vector and achieve the Nash equilibrium due to the increase of interference. Besides, we compare the performance of our algorithm with different minimum QoS thresholds. When the threshold is set to be 0 dB and negative 5 dB, the curves of learning efficiency perform well. When the QoS requirement is high, more steps need to be tried to meet users' experience. Lastly, the performance of training efficiency and the total QoE value of our algorithm are compared with several mainstream optimization methods. For the convenience of comparison, the curves of training steps in Figure 7 are fitted. Our algorithm shows better performance than the DQN and Q-learning method in terms of training speed and convergence. Moreover, we execute the simple genetic algorithm SGA as a classic method to solve the optimization problem. As the number of users increases, the total QoE utility increases and the three learning methods perform better than SGA and achieve approximately the same QoE utility. The DQN method and Q-learning method obtain less QoE utility when users of the system get higher, and it shows the superiority of our algorithm. Finally, we draw a conclusion. In this paper, we focus on the transmission of VR service based on the cloud edge and architecture towards future generation communication. For most, we formulate a joint optimization of the mode selection and resource allocation to maximize the QoE of VR users. Then we propose a distributed game theory-based deep reinforcement learning (DGTB-DRL) algorithm to conquer the high complexity problem, which can achieve a Nash equilibrium and maintain the adaptation capability and scalability. Simulation results shows the superiority of the proposed algorithm compared with the prevalent schemes in terms of training efficiency, QoE utility values. My presentation is over. Thank you for listening.